Unit 2, Day 16 Notes, Part 3. So the first thing they have, derivative of a polynomial function f of x is given by the equation. So they've already taken the derivative for us, and it's written in factor form. So on what intervals is f of x increasing, decreasing? Justify your answers. Well, the first thing I need to do is find out where the critical values are. Let's find out where the derivative equals 0. So we got three things, either x equals 0, and this is, so x equals 0, 2 minus x equals 0, so I can just bring the x over, 2 equals x, and then lastly x equals negative 3. Now, increasing the derivative must be positive, decreasing the derivative must be negative. So we need to do a sign change chart. So I'm going to, there's my negative 3, there's my 0, there's my 2. I'm going to choose negative 4, substitute it back into the derivative. So I'm going to get negative 4, 2 minus negative 4, that's 2 plus 4, that's positive. Again, I really don't need to know the value. I just know anything less than negative 3, they're either all going to be positive or all be negative. They can't be 0. And if some were negative and some were positive, then I'd have to cross through 0 and I'd have another critical value. Negative 4 plus 3 is negative. So I have an even number of negative numbers, so I'm going to be positive. So that means it's increasing. Between 0 and negative 3, let's choose x equals negative 1. And here I have x equals negative 4. So substitute back in, that's negative 1. 2 minus negative 1 is going to be positive. Negative 1 plus 3 will be positive. So I have an odd number of negatives, therefore it's going to be negative. So the derivative is negative, therefore the original function is decreasing. We'll show that in a second. Between 0 and 2, let's choose nice and easy, x equals 1. So that's going to be a positive value. 2 minus 1 will also be positive. And lastly, 1 plus 3 will also be positive. So they're all positive. So the original function is going to be increasing there. And we'll write those intervals in a second. And above 2, I'll choose 4. I chose negative 4 over there. So 4 is positive. 2 minus 4 is going to be negative. And then 4 plus 3 will be positive. So I have one negative value, an odd negative value, odd number of negative values. So that's negative. And I'm drawing these little lines just to kind of get us thinking min and max, because that's what number 17 and number 18 ask us to do. So I still haven't even answered the question. It says where are the intervals increasing, where are they decreasing? Well, increasing here, so it's going to be increasing when the derivative is positive, and that is between negative infinity all the way up to negative 3, and then again it's going to be increasing from 0 to 2. Alright, and now let's look at where it is decreasing. I'll write that down bottom here. It's decreasing when the derivative is less than 0. Where is it decreasing? It's decreasing between negative 3 and 0. And then union with 2 to positive infinity. Alright, and now let's answer some of the questions on the relative min and relative max. And we're going to use this same sign change chart. So f of x has a relative min. Let's write that down. F of x has a relative min. Actually, let me write down, and then you guys sort of finish up 17, where the relative minimum occurs when the derivative goes from negative to positive. That happens at 0. So there's my negative, there's my positive. So x equals 0. And then where does the relative max occur? That occurs when the derivative changes from positive to negative. So there's two of those. So up here in the sign change chart, it goes positive, and it has a derivative of 0, then it goes to negative, so it occurs at negative 3. And here, positive to 0, down to negative. So there's a relative maximum at negative 3 and positive 2. Alright, let's answer these last two questions here. So the first thing we have to do is find the point of tangency, slope of tangency, equation of the line, And then for number 20, we're going to use our equation of the tangent line from 19 to give us a good approximation of what the value of the function is at a point close to the point of tangency. So why don't we do that right now? So what's the equation of the tangent line? So the first thing I can do is find the point of tangency. That's actually given right here. So, because they're saying that x equals 4, well, when x is 4, I know the y value is -1. There wasn't a data table or anything like that. Now, the slope of tangency, I know what the slope's going to be at x equals 4 by substituting in x being 4 for the derivative. And remember, up front it was x times factor 2 minus x times x plus 3. So every place see an x, put in 4. So 4 times 2 times minus 2 minus 4 times 4 plus 3. Hey, that's -56. So once I know the point and I know the slope, I can put into the point slope equation of a line, y minus y1 equals m times x minus x1. Okay? And now to approximate, we're just going to substitute into this equation that I have right here. So y plus 1 equals -56 times 4.1 minus 4. I'm going to bring the 1 over. -56 times 0.1 minus 1. This is -5.6 minus 1. That's multiplying by 1/10. And that is -6.6. Okay, so they told us to approximate. We did that, and it says explain why this is a good approximation. So, hey, we say the value of the original function at 4.1 is approximately equal to -6.6. So, using the equation of the tangent line is a good approximation of f of 4.1 because the y value of the tangent line and the y value of f prime of x are close to the same. They're very close to the same at x values that are close to the x value of the point of tangency. So let's go on to the last page. Actually, before we do that, let's come back to our very first example here. I can see that the closer I am to the point of tangency, if I'm a little bit off, then the x values are a little bit off, the y values are a little bit off. But as I get further and further away, this tangent line is going to get further and further away of an approximation of the original function. So I'm getting further and further away in an x direction, then my y values are getting further and further away. So that's what number 20 was talking about. Okay, so let's look at where's the graph of the original function decreasing. They give us the graph of the derivative. Well, I know the original function is decreasing whenever the derivative is less than 0. So hey, -3 is the critical value. That's where the derivative is 0. And then not including the -3, but all the points from -3 to my next critical value, 0, not including the 0. And then that's union with from 0 to +3. Obviously another critical value there. Where is it increasing? So it's going to be everything that's above the x-axis. So from -infinity all the way, oh, I didn't write them down, -infinity all the way to -3, union with, right there, as we go up, 3 to +infinity. Okay? And now, when does it reach a relative max? When does it reach a relative min? Okay, where's the relative max? It occurs when the derivative changes from positive to negative, and in this case it's going to occur at -3. And let's look at what that looks like on the graph. So again, this is the graph of the derivative. Up here it's positive, and then we cross the 0 and it goes into negative. Therefore that's going to be a maximum value in our original function. The second to last question here, when does a relative min occur? It occurs when the derivative changes from negative to positive. So this is going to occur at x equals +3. Once again, let's go look. Here's the derivative. It's negative. Down here, it crosses through 0 and goes to positive. Okay, the last question here. Approximate the value of the original function p at 1.8, knowing that the tangent line approximation, using the tangent line approximation, if I know that P of 2 equals negative 3. So they had to give us this, and we know that 1.8 is close to 2, but x is 2 when y is negative 3. That's going to give us our point of tangency. I know that the derivative at 2 is equal to negative 4. Oh, I meant to come up to this chart. So when x is 2, y is negative 4. Remember, this is the derivative. That's the value of the derivative. We're not taking the slope of the line. This is the slope of the line of the original function. Okay, so that's what I know. So next thing I did was do point slope, point slope equation of a line. I normally wouldn't have to simplify it, and I'm not going to here because I want the approximation. So now I'm just going to substitute in y plus 3 equals negative 4 times sum of 1.8 plus 2. That should be negative 2. Good thing I caught that. So my x value is positive 2, and it's always y minus y1 equals m times x minus x1. And now I can simplify this. So let's bring over the 3. That'll be negative 0.2 minus 3. Negative 4 times negative 0.2 is going to be 0.8. That'll be positive 0.8 minus 3 equals negative 2.2. So I just found the approximation of p of 1.8 as approximately equal to negative 2.2. So good luck on homework 16.